so what I wanted to do here is go over Shannon's paper and highlight some of the features that if you have not read the paper, certainly everyone should know. But if you have read the paper, maybe rediscover some of the things that we find more interesting. And also I'll tell you a few side stories along the way. So here's the cover of the official reprint of the paper that appeared in 1948. Of course, it's very rare that a scientific discipline has a birthday, and in this case was July and October 1948. And this is really the time of mathematics. And of course, everything we do nowadays in the information age is thanks to this paper. Mathematics had, of course, had played already a role by 1948. There were systems like the Wiener filter, the Max filter that had been obtained thanks to the solution to an optimization problem. And analyzing those systems, of course, gave you the answer of what was the best possible that you could do. Now, Shannon went beyond that paradigm of posing an engineering problem as a mathematics problem, in the sense that he was able to tell us what the fundamental limits are without necessarily being able to actually solve for the best possible system, which the problem is so complicated when you pose the problem as to what is the best encoder, what is the best decoder, or a data transmission system, or a data compression system. The problem is so complicated you cannot actually solve for the argument that maximizes the performance system, the performance penalty, but he was able to, in fact, find out what the fundamental limit is. Okay, so let me tell you a little bit of the gestation of this paper. It really started back at the time when Claude Shannon was a graduate student at MIT. He wrote what is called the most important master's thesis of the 20th century, which was the application of Boole's algebra to the design of computers, of logic circuits. Something that sounds like, well, how come nobody thought of that before? But he was indeed the first one. Then he was, his PhD thesis was unpublished, was a mathematical approach to theoretical genetics. But already there at MIT, he was thinking about communications problems. He had read some of the papers by Hartley and Nyquist, and was already thinking about those problems back there, even if in his research he really didn't have any opportunity to think about communications. But here's a letter that he wrote to Vannevar Bush, who was essentially was his boss, the person who had recruited him to MIT. I think at some point he became provost or president of MIT, and then he was quite high up in the defense establishment during World War II. So he wrote him this letter when he was 22 years old. And there he tells him that he's been thinking about communication systems in this mathematical way. But what is very novel and very striking about this way of thinking that he outlines in this letter is that up until then, communication systems were instantaneous devices. Just think of AM or FM or television and so on. So you could think of a processor that at each time instant looks at the message and then transforms it into another value. Whereas here, these boxes, in fact, look at the whole message that you want to transmit and then produce a waveform. And the same thing here, you look at the whole waveform that you have obtained, and then you produce a guess for the original message. So, of course, that is the bread and butter of the formulation of information theory problems, and it goes back to his PhD days at MIT. All right, so then he moved to Princeton. He got a postdoctoral fellowship at the Institute for Advanced Study. And this institute, as you probably know, this is where Einstein was and where von Neumann was, and so on. He was working under Hermann Weyl. In fact, he was basically working on his own. And he said later on in his life, he said that the concept of entropy, for example, he started thinking about that concept here in Princeton. All right, then from Princeton, he moved to New York. He was working in Bell Labs, in the West Street location of Bell Labs. So I always thought that information theory actually saw the light in New Jersey, like many other things in communications, like the Morse code and the transistor and so on. They were born in New Jersey, but in fact, information theory was born in New York because he was one of the last people from the labs to move to Murray Hill. He actually liked living in the West Village. So, so this was actually the largest research building in the world. It was the Manhattan side of the Manhattan Project. So he had been working quite heavily on cryptography during the war. And he had befriended Alan Turing, for example. So of course his work in cryptography and his work in information theory happened at the same time. He wrote a very famous paper, which has the most famous theorem in cryptography. The fact that if you want ironclad secrecy, you really need to have a key that is as long as a message. So he wrote that paper that was classified shortly before the 1948 paper. And that's where the concepts of entropy and so on appeared for the first time. So then, in 1949, then he moved to Murray Hill. This is a picture of how Murray Hill looked like in the when it was first built. And of course, the transistor essentially was invented the same year, 1948, as well as the Hamming code, by the way. All right, so here's a picture of Shannon that appeared in Life magazine. So he became a celebrity almost overnight. Those were the days when research was really something that was glamorous. So it was kind of like the aftermath of World War II, that to a large extent had been won thanks to research. You know, cybernetics and communications and electronics and all that had a big allure for the general public. Now in electrical engineering, we're struggling to get undergraduates interested. We're going to go into financial stuff. Now, let me show you a picture here that was taken in 1962. And this picture was taken by Henri Cartier-Bresson, who was the most famous photographer in the 20th century. And it appeared in a magazine called Vogue, which right now I don't know whether you've seen it, but they don't have features on researchers or professors. More like Nicole Kidman, which I don't mind. So here's Claude. This was taken somewhere in a room at MIT, and this picture has only become available online in the last few months. Now let me show you another picture, which I have to go to the right for that. Here's a picture from 1944. So this is when really he was already working in this paper, on this paper. So he was 28 in this picture, and this was his girlfriend. He had been married in Princeton to his French tutor. He had an 18-year-old French tutor and they married her, but the marriage didn't last too long. And then this was his girlfriend. She wrote a book, Graphotherapy, which is where this comes from. And looking at this picture and how good this paper that he was writing at that time makes me want to go into a low-calorie diet. All right, so let's go back to this, and let's get now into business about following this paper now. So what I'll do, this is from the original typesetting of the paper. That in order to be able to show things on the screen on a more conveniently, I'm actually going to show the LaTeX version of the paper, which Emre Telatar, for the 50th anniversary, he had the foresight of LaTeX paper. All right, so you notice here a little difference. This was a mathematical theory of communication. This was the paper that appeared in the Bell System Technical Journal. And then here, there is the cover of a book called The Mathematical Theory of Communication. And this was reprinted by University of Illinois Press. And they appended to it some expository paper by Warren Weaver, generalizing the theory to the broad problem of social communication. So many people refer to information theory as Shannon and Weaver's information theory, or they talk about Shannon, Weaver, entropy, and things like that, which is, of course, nonsense. Weaver had nothing to do with information theory. But that was, for some reason, Weaver had been Shannon's boss in one of the early days at Bell Labs, so I don't know why they did this, but it's really a paper that doesn't have much to anything. Anyway, so here's the first paragraph in Shannon's paper. So he says PCN, PPN. Interestingly, in fact, when he got elected fellow of the IEEE, which was after 1948, his citation for fellow of the IEEE was for elucidating the theory behind PCN rather than information theory. So it's kind of like Einstein getting the Nobel Prize for the photoelectric effect. So he says a basis for such a theory contained in the important papers of Nyquist and Hartley. Now Nyquist had written a paper that has nothing to do with the Nyquist theorem on how fast you could transmit a signal, how fast you could transmit information through a linear system. And then he came up with the conclusion that it should be proportional to the bandwidth of that system. And then Hartley, 1928, he wrote a very beautiful paper that contains only one equation. Actually, when you read that paper, it has very modern language, like intersymbol interference, capacity of a system, information, and so on. But it's very descriptive, nothing really mathematical. So then he says, in the present paper, we will extend the theory. Extend, this is like the understatement of the century. He was a very modest man. And then he goes on to explain what the fundamental problem of communication is. When he says reproducing at one point, either exactly or approximately, a message selected at another point. Now when he talks about points here, talks about points separated by distance, data transmission, or points separated in time, storage. All right, right, then he goes on to say something that I find quite humorous. He says, frequently the messages have meaning. This was before Facebook. And then this sentence, the semantic aspects of communication are irrelevant to the engineering problem. Now this has been a source of enormous amount of flack, and especially from social sciences. They say, oh my God, these engineers are only interested in meaningless bleeps, you know. And so here, you know, really, well, this is one of the great successes of information theory, that we don't worry about meaning. Okay? We are very cold-hearted. But you know, there are people who actually insist that there should be semantic information theory. So they like to look for meaning in all the wrong places. All right, so the significant aspect is that the actual message is one selected from a set of possible messages. Okay. Now, then he goes on to argue about the logarithm. In fact, Hartley had already argued that if you want to measure information, then you should take the logarithm of the number of possibilities. And then he says, well, really that's what we should do, but when we go to cases where the statistics of the messages are involved, or we have a continuous range of messages, analog messages, then we'll have to generalize what Hartley told us. And then he says, well, we have to choose a basis for the logarithm, and if we choose the binary base, then we have base. And that's a word that had been suggested by Tukey just a few, in fact, just a few months before. Tukey was working in Bell Labs, and then he joined Princeton in the statistics department, which no longer exists. Anybody knows what Tukey is famous for, besides inventing the word bit? The FFT, right? Cooley Tukey. Okay. All right. So here's the coat of arms of information theory, and it's figure 1 in this paper. Now, again, you can see here that the thinking that he had in 1939, when he was a graduate student, is already there. And here he has this little box. The little box is the channel, and then he makes it clear that channel is in fact affected not just by the signal that goes in, but by various noise sources. So, in fact, you don't find a diagram like this before in the communications literature. So as I always say, you know, it's very easy to do something new. It's very easy to do something simple, but it's very hard to do something that is both simple and new at the same time. And this was it. Now, let me show you the 21st century version of this from our friends from computer science. And this is how they depict this diagram now. So I really cringe every time they have to say that the transmitter is Alice and the receiver is called Bob. And of course there is nothing in between, right? So there's just a straight line. All right. So then he says, there are 3 types of systems that we will be interested in: purely discrete, purely continuous, and mixed. Now, purely discrete, think of say, compressing a file, compressing a text file, and just store it in memory. Continuous, just think of television, but the television in 1948. So analog signals converted into analog signals. And mixed, think of, he gives the the example of PCM. PCM is of course the compact disc standard. But other types of big systems is satellite radio, Sirius. The phone, the telephone, because the telephone is using PCM. Or television nowadays is digital television. Okay. So in fact, since 1948, the middle part, the discontinuous part, has really been dying, and there are fewer and fewer systems that abide by this just continuous paradigm. What is the reason why continuous systems, we design them nowadays as mixed systems? So we take analog signals, we make them digital, and then we make those digital signals analog signals again, because the medium is inherently analog, like for example the wireless medium. And then we do the same thing, and the receiver digital, and then digital becomes analog. Okay, that's like when we call our cell phones. Well, Shannon never tells you that that is, that's what you should do, and a system that is purely continuous wouldn't work. But in fact, it's a very good pragmatic way to design systems. If anything, because then you separate the tasks of compression and transmission. And you can have an expert who knows about compression, and then another expert who knows about transmission. All right, so then he starts the meat of the paper, what he calls the discrete noiseless channel. In fact, there's really no channel there. So think of here, he was very much influenced by the example of telegraphy in this first part of the paper. So we tend to think of Shannon's contribution in 1948 as having three legs: lossless compression, data transmission, and lossy compression. In fact, it has four legs, and the first leg is the first one, and it's the one that has had the less impact in practice, even though it has had impact in practice. So the idea here is, first he gives a special case. He says, well, if the symbols have unequal duration, how many different messages can I pack per second? And then he gives, he calls that the capacity of this discrete channel. And then he gives a formula for that as the largest real solution of some equation. And then he goes on to generalize that when, in fact, not every sequence is allowed. So in fact, now we have to introduce redundancy, just like when you introduce redundancy in an error-correcting code. But now it's not because we want to find some possible noise. There is no noise here. Now it's because some sequences are not allowed. And of course, that's what happens in telegraphy. In telegraphy, you may have a diagram like this, where after a dot you can have a dash, after a dash you can have a dot. But after a word space, you cannot have another word space. Then you would have to have a dot or a dash. Okay? And it's very remarkable that in that paper he was already thinking of this, because in fact this has become extremely important for the technologies of storage. Right? Because in storage, because of the physics of the reading technology, you cannot allow just arbitrary sequences of zeros and ones. For example, you may have to have a certain minimum number of ones or a certain minimum number of zeros. Okay, so then he gives the solution to the general problem as a determinant being equal to zero. And in fact, what I want to point out here is that in 1948, in this paper, he was not using matrix notation. So this delta ij, what that means is an identity matrix. In fact, there are other things that he wasn't using back then either. For example, the word variance never appears. It's all standard deviation. In fact, variance was a relatively modern term. The word covariance matrix does not appear either. Okay, so now let's go back now to the second part, the discrete source of information. So now he says, how are we going to model sources, for example, English, mathematically. Okay, we're going to model these discrete sources mathematically. And then he said, well, how about using joint probability distributions, or just the conditional distribution of a symbol given a fixed length string of the past. All right, and then he says, well, let me make a case for the fact that if I allow myself to look further and further into the past, then I'm going to be able to approximate English, a natural language, better and better. And then he goes to some effort in doing these simulations where he says, well, what happens if I first draw letters equally likely from the alphabet? And then he gives us a sample path of that. And then he's going to say, well, now let me not just do a zero-order approximation, but let me draw letters according to their frequency in English, but independently from each other. Okay, so this is what you would get. And then he says, well, what about second-order approximation? So in other words, now, what we do is we have the right consecutive joint distribution of letters. Okay, so now we already have words that are valid words in English, like Andy and R and on. So you know all these paragraphs that he has are very good sources for passwords. Okay. If you're in need of passwords, you can work with this. All right, so third order approximation, now the trigram structure in English. Now, of course, now we start having more interesting words like reptaging here. This would be a very good name for some kind of medicine. Temperatures, on and on. I'm sure that if you go to the web, you can find the meaning of all this. All right, let's do that. Wow, look at that. How come this is so slow? I'm a collector of vocabularies. Oh, the made-up word mononym was invented many years ago in one of the first computer experiments that studied statistical structure of English. It's like an All right. Very good. So now he says, all right, good. Let's quit this, and now let's do this not with letters but with words. So now, how would you do this? How would you, the dictionary doesn't exactly tell you what the frequency of each word is in English. So what he did was he just went, open a book at random, and then he selected the first word in the page. And then, what is the next thing? The next thing is to do that, but with second order word approximation. So now, the game would be the following. So now you get the first word by the procedure that I just explained, and then you look for that word later in the document and find what is the next occurrence of that. What is the next word following that word, and so on, so forth. And then he gets this. this example. Okay.
So did he do this manually or?
Yeah, manually, of course. I mean, back then you would not think of just having a deck of cards and going to a computer. Yeah, 1948. So I think some of the poetry in the New Yorker is composed in this way. They had an frontal attack on an English writer that the character of this one. This is plausible. Alright, so now we have commercial interaction here. This was an ad for a Daisy Wheels printer. This is how the printers look like when I was a graduate student. And I want to show you something here because you see the print speed in this ad says 32 characters per second channel text. In fact, what happened was that this text that we came up with in the paper became a standard text to test the speed of typewriters. Because you see, you wanna have words that actually are feasible words in the English alphabet. Because when you go in these typewriters, when you go from one letter to another letter, the speed depends on which actually pair of letters you have. So that was the standard way in which typewriters were measured, were tested. All right, so then he goes on to say, look, what we really were doing here by looking at a finite history of the process is really the Markov process. Okay? He uses the French spelling of Markov, and in fact, this is a paper that appeared in 1956 by a young man from MIT, Noam Chomsky, who is, of course, the father of modern linguistics. And this paper appeared in the Information Theory Transactions. And he says, no way, Jose, you cannot approximate the English grammar with a Markov process, no matter how long that Markov process is. Okay, so that's a paper that came before his revolution in modern linguistics. But the truth of the matter is that nowadays, the problems that where we know how to compress well are really problems that exploit Markovity in the source. Like, for example, the belief among experts in lossless compression is that we ought to be doing a better job at compressing images than we're doing nowadays. And in a way, it's because we're very much wedded to this Markov thinking. When we prove theorems that go beyond Markov structures in information theory, in fact, we prove them generally by doing Markov approximations. All right, so then he comes and tells us about ergodic and mixed sources. In fact, when he says here ergodic, in fact, he means Markov, ergodic Markov chains. So fully connected and aperiodic, and what is the other thing? Positive recurrent. Although in this case, he's just thinking about finite processes. And then he talks about mixed sources. Mixed sources meaning non-ergodic sources. So non-ergodic information theory actually started in 1948. All right, so then he says...
Sergio, mixing is our mixing sources, or what does it mean?
No, not in the sense of, of phi and so on. No, it's in the sense of the ergodic decomposition theory. Okay. The fact that we can express a stationary source as a mixture of stationary ergodic.
But for Markov or non-Markov also?
Well, yeah, I mean, he was thinking of a mixed source where the components are Markov.
So reducible means, for example, periodic Markov. Okay.
Yeah. All right, so then he says, can we define a quantity which will measure, in some sense, how much information is produced? and what rate of information is produced. And then, then he has this axiomatic introduction to entropy. And this, in fact, has done more harm than good to information theory, because people who are outside our business, when they think of this paper, think of Shannon coming up with the notion of entropy as the big achievement of the paper. And in fact, our discipline is not about definitions, it's about theorems. It's about posing problems that are of interest of an engineer. What is the best algorithm that you can come up to do such and such? And then showing that the answer to those questions is in fact an answer that happens to involve information measures such as entropy and mutual information and so on. So in fact, we don't need to justify entropy in any way just by the fact that it is the right answer to the problem that we're interested in. And he in fact says that. He says, this is in no way necessary for the present theory. It is given chiefly to lend a certain plausibility to some of the later definitions. The real justification will reside in the implications. So that's the real thing. Okay, so then he says, well, with those axioms, the only thing that you can have to satisfy the assumptions is a function that looks like that. Now, of course, here's the thing. Now, physics. Of course, physicists, a lot of the physicists say, oh yeah, Shannon, 1948.
So, Sergio, question. Is it the first usage of information theory, the previous slide?
Oh yes, in fact, I wanted to mention that.
You see, I'm helping you.
Yeah, thank you. So this is the only place in the paper where the phrase information theory starts. And many people think that information theory was not coined in 1948, but that came out later. In fact, it came here in this case. Now, later on, he was kind of very reluctant to actually use this term information theory. He thought, partly because it had been overused, and there was a lot of bullshit that in fact had been written under the banner of information theory. So originally he called it communication theory, and then later on, in some of his later papers, called it either communication theory or even coding theory, which of course now has a different connotation of being more constructive side. Okay, so then of course comes the physics connection. So then he says, well, this is what the H in Boltzmann's famous H theorem. Now, let me just parenthetically say that H, which we use universally for entropy, in fact, Hartley, in his 1928 paper, when he was talking about just the number of messages, the logarithm of the number of messages, he also called that H. But I think that was fortuitous, nothing to do with Boltzmann. In fact, Boltzmann never used H in any of his papers. So Boltzmann, this is the paper by Boltzmann in 1877. What he did here, of course, they were interested in gases and so on. But he said, well, just as a thought experiment, let me think of these gas particles as living in discrete places in space, not in an analog world, but in a discrete world. And then he finds the probability of a typical sequence. So this is how, as close as Boltzmann came up to writing the formula for entropy. But in fact, when you go to Shannon's paper, you see this footnote here of a book by Tolman. And Tolman, what he does there is to express the Gibbs, Boltzmann-Gibbs type of setup in quantum mechanics. So now we go back to a finite number of possibilities, and in fact, in that book, you find exactly the formula. You find sum of P log P in that book. Okay, entropy, in fact, the word entropy, with a different meaning, had been introduced earlier by Clausius in 1865, and then it was Gibbs that found a relationship between that concept and what we now call differential entropy. Okay, so then he gives some of the basic properties of entropy. Now this one is very interesting, because now we will be able to prove this theorem very simply with relative entropy. The fact that when you have a doubly stochastic matrix and the entropy at the output is going to increase. But you know, he didn't have the tools of convexity. He didn't have Jensen's inequality does not appear at all in his paper. Okay, but then somehow he was able to prove that. Okay, he defines conditional entropy. He uses this notation for conditional entropy, which we don't use nowadays. And then he comes to a discussion of two extremes in the redundancy in English prose, represented by basic English. That's like a vocabulary of 800 words. And James Joyce's book, Finnegan's Wake. Now he was really taken by that book, which had appeared just 10 years before or something like that. And in fact, that picture I showed you before with the girlfriend in the 1944 bikini, that book actually has a dedication of a book called A Guide to Finnegan's Wake. It's a dedication from Claude to his girlfriend. So I don't know whether you've ever opened that book, but that's certainly something that is quite a pleasant read. I let you read the beginning of Finnegan's Wake in a few moments. This is the example, remember, of highest entropy of the text. So, you know, if you're able to read this cover to cover, I think you can put it on your resume. So in fact, James Joyce, when he wrote this, he said, this is going to keep the professors busy for many, many years. And in fact, in a way, that's what Shannon did with his 1948 paper. He's keeping the professors busy for many years. But, wow, Shannon really was a big fan of James Joyce. And in fact, here's a picture of Shannon's office, home office. And anybody sees something here? Peculiar? Well, he was not, he liked entropy, as you can see. So this gentleman here, this gentleman with the funny hat, that's James Joyce.
It's not Hilbert?
Eh?
It looks like Hilbert.
It's James Joyce.
This is his office in MIT? Or
No, this is his home office.
Oh, home office.
Yeah. That must be, I guess, having such a prominent place up there, probably his mother and his father, I would say. I would think, maybe, I don't know. Okay. So here comes another interesting nugget. He says the ratio of entropy to the logarithm of the number of choices, I'm going to call that relative entropy, something that is between 0 and 1. And for many years, I refused to call relative entropy because, I wanted to pay homage to Shannon and say, okay, is Shannon called relative entropy something different? I'm going to call divergence or Taylor, whatever. I'm not gonna talk related to that. In fact, now I can change my mind, and I love to call the divergence relative entropy. I think that's the right name for it. All right, then he goes on to this paragraph. There was, in fact, a whole Shannon lecture by Jack Wolf devoted to one paragraph in respect to this paragraph, trying to reconstruct what did he mean by this, because he says that just because the redundancy of English is what it is, that we can have interesting crossword puzzles, because the redundancy is about 50%. If it were 33%, then three-dimensional crossword puzzles should be possible. But these numbers, well, nobody really knows where he came up with this. All right, so then he goes on. You know, it's very interesting because now, when we teach information theory, when we teach lossless data compression, of course, we teach it first for memory resources. And then, of course, if the audience is sophisticated enough, then you may also mention the Markov case. Shannon said, who in their right mind would want to compress a memory resource? So he did it directly for Markov sources. Okay, so all the results that he has there are for Markov sources. Then he has the usual properties that link conditional entropy to the entropy of a chunk. And then he comes to the first occurrence of this word, typical. And that, of course, can play a very important role in his development. The fact that he was only going to think about things whose statistics were close to what the statistical laws would say they should be. All right, then gives this theorem, which he proves rigorously, and this is, of course, what we call the asymptotic equipartition property for the case of Markov chains. Okay, so the typical sequences exhaust most of the probability, and their individual probabilities are roughly the same according to this formula. Okay, so then he goes on for the case of the Markov chain, to actually compute their probabilities. In fact, there is a typo here. There is a capital TI is in there. I'll tell you a few more, since we are here on a small audience, and this is not going to come out of the room. I'll point out some other mistakes. Okay, and then he gives the strong form of the theorem, saying that regardless of whether you are prepared to take a hit of not finding your message in the code with probability 0.99 or probability 0.01, the fundamental limit is the end. Okay, so this is in fact what we call the strong converse. And in fact, he says theorem 4 follows immediately from this, calculating upper and lower bounds for MQ based on the possible range of values of P in theorem 3. Now, the achievability is true that follows from this. The converse does not. So we have to do more work. I didn't show how it was done. All right, so that brings me to Duke's review that appeared right after. Duke was like the dean of American probabilists. And look at what he says. He says the discussion is suggested throughout rather than mathematical, and it's not always clear that the author's mathematical intentions are honorable. So that's a pretty nasty thing to say. And in fact, American probabilists were very slow in realizing how good what Shannon had done was, how revolutionary. It was really David Blackwell, the first one, to understand how good it was. And whereas in the Soviet Union, they were much quicker to realize how good it was, and Andrei Kolmogorov in particular, and then they started a very solid mathematical school of information theory with Hinchi and Kolmogorov and so on. So, I mean, there are, you have to view that paper kind of like in the context of its time, and also in the context of where Shannon was publishing it, which was really a publication, Bell System Technical Journal, that was really a publication for engineers. So the paper is extremely easy to read, but the price he pays is that he's not going to give you a detail for everything he says. Okay. And it's pretty remarkable that his amazing intuition was such that, in fact, it took the professors years to actually formalize what he had, but for the most part, everything he said was correct. All right, so here's the formula for the entropy. For the minimum achievable source coding rate. You know, in all these years, we haven't come up with a word as nice as capacity for the fundamental limit of the source. And he gives that for the mixed source. All right, so then he, unfortunately, now we can, going back, we can say, well, he shouldn't have done this, he shouldn't have done that, with the hindsight of time. So, of course, it would have been much better if you would have considered the case of lossless compression without talking about channels at all, talking about capacity at all, and vice versa. Channels without worrying about sources. But he didn't, and so he kind of like had both things simultaneously, so now he has the noiseless channel. And then he says, source has entropy H, and the channel has capacity C, but this is a bit high. And then he says it is possible to encode the output of the source in such a way as to transmit at the average rate C divided by H. So now the rate now is the inverse of what we think when we talk about the data compression rate. Okay, so in terms of compressed symbols relative to source symbols, so now this is source symbols relative to compressed symbols. So we can do it if it's less than C divided by H. We cannot do it if it's greater. Now this is the first time that the word converse appears in information theory. And of course it has stuck in the sense that it means it's a theorem that tells you what you cannot do. It's a theorem that applies to every code. Every code must have some property. That's a converse rather than yes.
So, there must have been some constraints on the channel because we have results that you can send at a rate above the channel capacity without separating the source and channel code.
Yeah, so as I said, this is, forget about channel, there's no channel here. It's just, think of C as being one bit per second, and that's it. All right, so ladies and gentlemen, the bad news is that the converse is wrong. So it's not just that he didn't give a result, but the converse is wrong. And the reason, there are two reasons. One reason is that Shannon, in his paper, he never considered prefix codes. It's very clear from everything he's doing there that he's never considering encoding symbol by symbol. He's always considering his usual paradigm of encoding strings into strings. Okay, so when we know that, that the minimum average compression rate lies between the entropy and the entropy plus 1 bit, that is of course under the assumption that we have either a prefix code or what we call a uniquely decodable code, symbol by symbol code. But if you don't put that condition, and in fact, many of the codes, like lentil zip, does not satisfy that condition, then in fact, on average, you can beat the entropy. Okay, that's one reason. And the other reason is that, in fact, here the rate is really the inverse of the rate. Okay. So in fact, you cannot even claim this, even if you were thinking of prefix codes. Okay, so now he has this formula, but this is maybe what has fooled people into thinking that he actually proved that. But to prove that, you really need graphs inequality that didn't happen until later. Okay. So this is a mistake that, for example, Wojtek does, that he attributes that result to Shannon, even after I Okay, so this is only for the Shannon code. So this is a very clever procedure that he had. But even the Shannon code here is not done on a symbol by symbol basis. It turns out that that is a prefix code, but it's not done on a symbol by symbol basis. Okay, notice that he says messages of length n. Okay, the message of length n, and then he applied the Shannon code to each string.
Well, Sergio, I prefer that just like giving credit for other things that he was aware of, that was not explicit about, here too, you may have had in mind this prefix condition. You didn't want to belabor the point or confuse them.
So then you are thinking that in fact not only that, but in fact he already knew how to prove it using graphs inequality, because that's the only way we know.
But why don't you give credit for that? For maybe having all that.
Okay, so there is the possibility that in fact you already knew that. Okay, but that doesn't mean that the theorem as is there is true, because even if you are in the prefix, even if you were under the prefix condition, the problem is that the rate is defined as the inverse. So then you would have one inequality going in one direction, and the other one, thanks to Jensen's inequality, going in the other direction. Okay, so now we come to channel capacity, and then he defines unconditional minus conditional entropy. He doesn't define that as the mutual connection. He calls it, he likes to call it the rate in that paper. All right, and then he explains the role of this hx given y, conditional entropy of the source given the message, with this diagram. So in fact, in this diagram, there is nothing here, it's just a straight wire. So you send the source kind of like uncompressed to this, there is a channel here. And then the work is done by this observer and the correcting device. So the observer looks at the input and the output. So in fact, it would have been better to call this the channel rather than the receiver. Okay? So the observer looks at the output of the channel, and then sees, for example, just think of a binary symmetric channel. So the observer could see where the binary symmetric channel has made the mistakes, has introduced the errors, and then he would tell the correcting device where those errors happen. And since those errors don't happen IID with probability 1/2, otherwise the capacity would be 0, then you can compress that sequence that tells you where the errors happen, tell the correcting device, and then how many bits do you need here? So you need the conditional entropy of the input given the output. Okay, so here's another one of these things that we're going to do a thought experiment about what would Shannon say. So now, suppose that we would ask Shannon, what is the result that has happened in the last 60 years, 64 years, that you find more surprising? And the result, this is my guess on what Shannon would say, the result that he would find more surprising is that in fact, here, if I cut this wire, then I can do as well as if the wire wasn't there. The capabilities of the system to transmit information remain the same. And why is that? Well, that's because of the Sledgen-Wolf theorem. Thanks to the Sledgen-Wolf theorem that says that, in fact, when you have side information at the compressor, then having it at the, side information at the decompressor, having it at the compressor node is not going to lower your fundamental limit. So that is where I would put my money. That is the most fundamental result that was outside Shannon's paper. Okay, so here's another thing that I wish that he had done in this way, which is to define channel capacity as the maximal mutual information. So as I said before, what information theory is all about is asking questions and then finding the solutions that just happen to get information as the answer. So when you ask the questions, you don't, the questions are in fact in terms of the fundamental limits. You say channel capacity is the maximum rate at which you can encode information and still be able to decode it reliably. And then you formalize it using channels. Rather than calling the fundamental limit already something that has the answer built in. Among other reasons, because in fact, this is not necessarily true. So there are channels for which you can't express their fundamental limit as the maximal mutual information.
Did he use the word mutual information?
No. No. I believe that the word mutual information was invented by Fana. And in fact, for many years it was called average mutual information. So, in fact, in mutual information, sometimes they use it for the random variable whose expectation is what we call mutual information. But now we call that random variable information density, which is really a very bad name. Okay, so now he says it is possible to send information at rate c through the channel with a small frequency of errors or equivocation as desired. So either probability of error or equivocation. Remember the conditional entropy of the input given the output. Okay, so then he formalizes this theorem 11, saying again. Remember that he has both the source and the channel at the same time. So if the entropy is less than the capacity, then we can indeed have arbitrarily small frequency of errors. If H is greater than C, then he says it is possible to encode the source so that the equivocation is less than H minus C. But there is no method of encoding which gives an equivocation less than H minus C. Okay, so that this converse is kind of trivial, right? Because he is defining the capacity as the difference between H and the equivocation. But then, in fact, he goes on to claim the strong converse in the way that we know it today. Okay, theorem 12. In fact, here he has a strong converse. And again, there is really no argument to support this. And this was only proven later by Wolfowitz. It took quite a few years to prove this theorem. And in fact, Wolfowitz was unkind enough to refer to Shannon's, instead of Shannon's results or Shannon's theorems, we could call them Shannon's conjectures. It's a bit too hard.
So Shannon did prove it? No. But he stated it.
Yes, this is.
So why he put a theorem and he didn't say he must know the proof?
Well, if you take Saki's philosophy, then
But it makes sense. It makes sense. If you put theorem, it means he must know the proof. Otherwise, why put theorem?
Hey, okay, I'm not going to argue about that. All right, so here's probably one of the highlights of this whole paper. In fact, the good Tom Cover used to say, if I had been Shannon and come up with the idea of random coding, I would have to go home and sober up. So this is the probabilistic method. So the idea of the probabilistic method is very simple. You want to show that some subset that you define in some way is non-empty. Okay. So then how do you do that? You do that by importing a completely artificial distribution on that set, on that whole set. And under that completely artificial distribution, you show that the probability of that subset is positive. So if the probability is positive, the subset has to be non-empty. That's the whole idea of the probabilistic method. So then he uses that here, in fact, in an embodiment that says, I'm going to average error probability over all possible codes, and if I find a code whose error probability is less than some number, then there must be, if I find that the average is less than some number, then there must exist a code whose error probability is less than that number. Now, again, he didn't do this with all the epsilons and deltas. He gave a diagram and he explained it by this idea of all the set of messages, there is a set of high probability messages. Again, this is coming back to the idea of typicality. And for every output that we have a set of possible messages that are plausible. All the others would not be plausible. All right. So in fact, if you look at, say, Cover and Thomas, the way that the channel coding theorem observability result is proven is very much following this and carrying it kind of mathematically. So essentially what you do is having a test for typicality that has three different components: typicality of the input, typicality of the output, typicality of the joint input-output. In fact, you can do it. That's not the best proof. You can do it much more easily just by comparing just the information density between the input and the output with just one threshold, rather than 6 thresholds that the other problem wouldn't create. Now, he tells us, in fact, in this calculation, he tells us what is the probability that there is an impostor. In the sense that if there is an impostor that passes the test, then he has this foresight of saying, well, if there is another guy who passes the test, in addition to the true guy, then I'm going to declare an error. I'm not even going to try to say, there have been several messages that pass the test, maybe I'll just pick one at random. If not, I'll just declare an error. And that's, of course, what we do in the usual proof. The thing that he doesn't do here is actually take into account the probability that the true message is not going to pass the test. Okay, so, because in his mind, anything that is atypical has 0 probability. Okay, and then there's the other component that he realizes that once he has shown this capability of random coding as being the way to prove the achievability result. Now let me just make a little parenthesis here. 1948, good codes are not known. In fact, codes that were able to come close to the capacity only happened in the last 10, 15 years. Bad codes are not known either. In fact, the Hamming code can be invented just by right then at the same time. Okay, so think of the tremendous achievement that it is to actually be able to formalize this problem and to come up with a solution at a time when nobody knows any code other than the Aster repetition code.
So are you claiming the probabilistic method were invented by Shannon, not Erdős?
Okay, so the probabilistic method was introduced by Erdős in 1947, but in fact was introduced even earlier in the Soviet Union. by, by another fellow. I'll tell you later. All right, so then he goes on to say, it's not just that by random coding I can find the code, but in fact, if we use random coding, then with overwhelming probability, the code that we're going to find is going to be a good code. Okay? So if we hire a monkey to choose the code for us, then with very high probability, we'll find the code. Now, of course, that is not the end of coding theory. Coding theory was not even at its infancy, as I was saying, it was in fact in utero. The problem is that it's not just finding a code that works. In order to be able to encode it, you have to have structure. You have to have an algorithm that is able to do that. And just listing the code books, that's not an algorithm, because the number of code books, of code words is going to be like 2 to the 10,000, for example. So that's not a valid algorithm. And of course, you also need the decoder, something that you can implement. And nowadays, the luck that we've had is that even if you are not willing to spend the complexity to go to an optimal decoder, you can come up with codes that have the right balance between the structure that they need to have in order to be able to be implementable and the random-like structure that Shannon says that they should have in order to come up with capacity. Okay, so I was saying before, when you were asking me about whether he had proven the strong converse or not, he said he had not proven the strong converse. But in fact, he didn't even prove the weak converse, what we call the converse that even if you allow arbitrarily small error probability, because you can't talk about capacity. So the converse that he showed was converse as far as not having, not being able to have equivocation that goes to zero. The equivocation, the entropy, conditional entropy of the input given the output, cannot go to zero. But from there, to claim that the probability of error cannot go to zero, you need Fan's inequality, and that was not available back then. Okay. And in fact, he never, in his subsequent papers, he never actually used Fan's inequality, he never referred to Shannon's inequality. In fact, he came up with his own inequality, which in fact I gave a talk in UCSD 98 a couple of years ago. It's more convoluted, but at the end of the day, it enables you to do the same thing.
So in this paper, it seems that he sort of identified new information with the problem of error already, right? He never really explicitly talked about problem of error. Is that correct?
No, in fact, he does. I mean, in fact, he does. So in fact, the achievability result, he really tells you probability of selecting the incorrect message.
No, in terms of the converse.
In terms of the converses, yeah. The weakness here is the converses. Converses for data compression, the converse for data transmission. Those are the things.
But it seems that he's implicitly assuming that somehow the neutral information argument can be translated to a problem error argument.
Yeah, of course. In his mind, it's like, okay, it's trivial, right? Because if you still have residual uncertainty, then that means that you cannot have a very good error probability because you're not going to have a point max. So, but of course, to formalize that rigorously, that's what Fan's inequality does. Okay, and then he says, if the source already has a certain redundancy, no attempt is made to eliminate it in matching to channel, this redundancy will help combat noise. This is a very savvy observation. And in fact, this is something that has been used in practice in the GSM system, for example. It's been used, and there are papers that look at this in quite a bit of detail. So we'll talk about the Shannon separation theorem that says that there is no loss by splitting the task of the encoder and the task of the decoder. encoder, the task of the source encoder and the task of the channel encoder into two separate parts. Okay, that's true, of course, asymptotically. It is not true non-asymptotically. There is something to be gained by doing things jointly. Now, we call that Shannon separation theorem, but in fact, Shannon did not prove that, because in order to prove that, again, you need the converse, at least in the almost lossless sense. In the sense of lossy compression, then it's a bit heavy, because then the result is almost trivial.
So how can redundancy help combat noise once you digitize everything? Once
Yeah.
you convert the source to bit?
Yeah, so in fact, that's what they did in GSM. So they realized that the vocoder had not eliminated all the redundancy. So then some zeros and ones were not really probability 1/2. So then you incorporate that knowledge at the decoder.
Source decoder.
At the channel
Channel
decoder.
decoder.
At the channel decoder, you incorporate that as side information at the channel decoder, and then you gain 0.5 dB or something. Joachim Hagenauer did that. That actually was implemented in Falls. Lambis also. All right, so then he says, here, let me give you an example of efficient coding. And this is the first channel with memory in the history of information theory. This is a channel that takes 7 bits, and then it's going to introduce one error, either 0 or 1 error. Okay, and all these 8 possibilities are equally likely. So then he computes the mutual information, the maximal mutual information for this channel. Of course, the best input for that is just equiprobable, and finds 4/7 bits per symbol. And not only finds the capacity, but then it gives us a code that achieves it. And what code achieves this? Yes, the Hamming code, due to R. Hamming. In fact, Hamming did not publish this until maybe a couple of years later. That was the first paper on coding theory. And then Golay, kind of at the same time, also had another very important paper. Now in Finland, someone came up with a very clever way to do soccer pools, and in fact that even predates the Hamming code, the Golay code. That's also a perfect error correction code, ternary error correction code. All right, so then he goes on to continuous information. And continuous information, then he says, well, here we will not attempt to obtain our results in the greatest general idea or with the extreme rigor of pure mathematics. Okay, since this would involve a great deal of abstract measure theory. But in fact, if you look at the appendix, it does have a very rigorous approach to the definition of mutual information, which is then what the Russians then adopted. And it really goes back to the definition of expectation as an approximation, as a discretization process. That really you don't need it. You don't need it because once you say, well, it's just going to be the expectation of a log likelihood ratio between the joint and the product of the probabilities, then you don't need to go back into that process. But he does have a rigorous approach. Okay, then he has this theorem 13, who actually he doesn't prove this theorem 13 here. He proves it in a proceedings of the IEEE paper that was published the following year, and that is the sampling theorem. Okay, the sampling theorem, Nyquist had nothing to do with it. Shannon was the one who came up with the expression Nyquist rate because he wanted to pay homage to Nyquist. But in fact, at the beginning of the 20th century, Whittaker already had something that was along these lines. Kotelnikov in Russia and Kuttmuller in Germany also had things that were along these lines. But really, Shannon was the first one to give a clean expression to the sampling theorem with the same factors. Now, it's interesting that, that in this part, continuous information, we're talking, Shannon is talking both about continuous time and continuous range. So in his mind, analog signals are continuous time. Okay, but it's very clear that why does he introduce this? Because he wants to work always in discrete time. And that's why information theory is essentially a discrete time theory. Okay, so here's one of the things that I like the least, which is the introduction of this measure of information as what he calls the entropy of a continuous distribution. Of course, nowadays, some people still like to call it the entropy. If you want to be more careful, you would call it the differential entropy. But in fact, this was all an artifact of the fact that at that time he didn't know relative entropy, he didn't know Kullback-Leibler distance, which by the way was introduced by Kullback and Leibler just 3 years after this. And the first thing they say in that paper is that their goal is to generalize that guy to the general case. So there are many reasons why one should abstain from using this. Anything you can do with this, you can do it more elegantly with relative entropy. And you cannot imagine how many people have fallen into the trap of thinking that this has the same properties as entropy. So for one thing, this can be negative, right? There are nice distributions that have negative differential entropy, and then of course there is the whole idea of the volume interpretation and all that, which is kind of like a placebo. But, I know that there are people in the audience who disagree with that. So anyway, here comes the differential entropy of the Gaussian distribution. Again, notice that he doesn't call it the covariance matrix, he says the associated quadratic form. Okay, he doesn't use matrix notation as I was telling you before. He uses that notation. I mean, this is kind of like saying, you know, how hard it was in 1948 to come up with all these edifices, because things that we take for granted now, back then were really kind of like very foreign to, especially to an engineer. You know? So it's even lends even more awe to our appreciation for Shannon's work. All right, so then he goes on to expressing the entropy power inequality. Now, the proof he gives in Appendix 6 is incomplete because it's based on an argument that is just purely it's just equating a derivative to 0, and you need more than that in order to prove that in fact you have a result of minimization. So it took a while to come up with a proof of the entropy power inequality. It was really the work Stan based on the drawing's identity, and then later on in recent years there have been more streamlined proof using some relationships between information measures and estimation measures.
So who gave the first proof? Could I do it?
Stan in the Netherlands.
What year?
59.
59?
Yeah.
Yeah, 59. And then Blackman is kind of at the same time. All right, so then he says in the analog case, then you would have that the channel capacity is as expressed as the limit as t goes to infinity, the maximum normalized mutual information. So this integral is more general than that, it says, because in this case, if you take differential entropy here, you would have infinity. You would have infinity minus infinity, or minus infinity minus plus infinity. Okay, then he goes on to give the capacity of the wide Gaussian channel with a certain limit. This is one of the most famous formulas in this paper. Now, Wiener published his book Cybernetics at the same time, and in that book, there is nothing about the concept of fundamental limit. But he says, well, Neumann told me that, in fact, it's a good idea to use this integral of P log P as a measure of information. So then he goes on to say that the Gaussian would be the largest, the one that would maximize that under a variance constraint. And then he goes on to, in fact, write a formula like this. Okay? And I'll come back to Norbert Wiener at the end of the talk. Okay, so now let me talk about a little footnote that he says, that he has in that paper, and that shows you again what a genius he was. He says, the name white noise, already firmly entrenched in the literature, is perhaps somewhat unfortunate. In optics, then he says, white light means two things. Either any continuous spectrum, as contrasted with a pointed spectrum. I didn't know that. Well, that sounds pretty striking, that anything that has certain bandwidth would be white light, because certainly it's not going to look white. Or a spectrum which is flat with a wavelength, which is really what we understand as white light. And then he says, which by the way is not the same as a spectrum flat with frequency. And that's the title of the slide here, white light is blue. Okay? Because if we think as white light as being flat in frequency, which is what we understand as white noise being, then you're going to have a higher spectral content in higher frequencies. Okay. All right, then he goes on to say what would be the capacity if the noise is not Gaussian. And this, in fact, he expresses in terms of the entropy power. But a nicer way to do this is to just say that the capacity is bounded, lower bounded by the Gaussian capacity, upper bounded by the Gaussian capacity, plus the non-Gaussianness, relative entropy between the noise distribution and the Gaussian distribution with the same variance. And then, finally, he comes to the last part of the paper, which is ray distortion theory. Okay, so then, in this case, he uses PCM as his paradigm. But PCM, of course, is a process that is instantaneous. So it does not exploit redundancy due to memory in the source. So, so then again, he comes up with a solution. And he comes up with a solution. Here he gives us a few hints of how he actually comes up with saying that the solution to this problem is the rate distortion function. And it's only several years later, 58, 59, that he actually writes a paper that has all the details in it. Okay, so rate distortion theory, in a sense, has lacked data compression by perhaps a gap of a few years, maybe even going back to the original papers. All right, so again, he has the result here. It says that you can do it provided that he again mixes the capacity inside, and it's not possible if the rate is above the rate distortion factor. In that case, the converse is really trivial. So in that case, the converse, we can grant it to him without any doubt. And in fact, the achievability, even though he doesn't give us all the details that later on gives us 10 years later, it is clear that he already knows how to do it. And the key to doing that is using random coding. Now, here, in this case, the random code is going to be selecting a set of reproduction points sampled from the output distribution that corresponds to the joint distribution that minimizes the mutual information under the rate distortion constraint. So I think it's fair to say that of the three main topics that he introduced, this is the one where the gap from theory to practice is still the largest one. So, yeah. MPEG, JPEG are designed using information theory, but still there are we have to cope with the fact that unlike the other two problems here, what we're trying to do is pull the human eye and the human ear, and we still don't understand how those work very well. So hopefully one day we understand that better, we'll be able to use distortion measures that are better than just say signal-to-noise ratio and so on. Okay, and then he gives, again, the rate distortion function for the Gaussian source, again, in the setup of continuous time. All right, so that pretty much brings us to the end. There is some other stuff that he does in the appendix and so on, but I'm going to skip the details. Let me just say that in the acknowledgements, it says, credit should also be given to Professor Wiener, whose elegant solution of the problems of filtering and prediction of the stationary ensembles has considerably influenced the writers' thinking in this field. Okay? And this is a paper that Norbert Wiener wrote in the IT Transactions a few years later. It says, information theory has been identified in the public mind along the theory of information by bits, as developed by Claude Shannon and myself.
What is the lesson here? Don't give anyone any credit.
Yes. That's exactly the lesson. Be careful with your acknowledgments. Curb your enthusiasm. Okay, thank you. Questions?
You could tell us about the reaction, the source of the probabilistic method?
Oh yes. So here's something I did. I gave a version of this talk in a school of information theory. It was organized by the IT Society a couple of years ago. So what I asked the students was, before we did the lecture, to send me an email with the answer to the question, what surprised me the most in Shannon's paper when I read it was blah, blah, blah. And then, if you want, I can show you some of the answers here. I think they are quite interesting. So, in fact, one of the answers refers to that. So, he says, I've read this paper several times since my undergraduate years, and every time I read it, I discover something new and fascinating that I did not realize previously. Right on the money. It gives you an idea of hope, as poetic as it may sound. Foundations of what we can expect from any communication system, giving us an idea of how marvelous a device can be. The essence of all that I know in information theory is contained in Shannon's first paper in the subject. It's true, many people say it's all in Shannon's paper. Surprisingly easy to read. That's very, very true. Which we've lost that ability. With time, we've lost the ability of writing papers that a large group of people can read. But of course, he did pay a price, and the price is that he couldn't put all the details there. So the clear engineering concept and the simplicity of the ideas and examples, that's again very true. How simple it is. And the fact that it's self-contained. One does not need to read another paper. In fact, the paper has very few references. And that, of course, is the nature of the beast, because he's starting a theory from scratch. So no wonder that you don't have to read a lot before you can understand it. Now this one says, seldom the case in today's publications where authors seek to obfuscate instead of illuminate the ideas of their work. Not all of them. Thinking made clear by examples from real data, such an English text. So this is what I was saying before, that was really, all the effort that was spent there, it's actually well spent, because it really opens people's eyes when you see something like that. The phrase, the theorem says that several times in the paper, where Shannon gives deep insight into what the theorem says. This is something that we don't do enough. We like to let the results speak for themselves, but we should do more of that, more of an effort in that direction. And then this one, this student actually had a hit a good point that thinking vaguely about a problem can be a very powerful tool. So, and in fact, it's harder to think vaguely than to actually think with all the epsilons and deltas. And in fact, this is really a primary example of that.
So Sergio, these comments are from students.
Yeah.
Yeah. Impressive students we have.
Yeah, and, well, but many of them were in fact from outside information theory. It was very wide. So it was really people, some of them had read this paper, but had not done a course on information theory before. Now, the semantic aspects of communication are irrelevant to the engineering problem. Unfortunately, his little concession has had very far-reaching consequences, and is nowadays still often used to diminish and even ridicule the importance of Shannon's insights, especially by communications scholars from social sciences. So they often quote this as proof that their point that communication is much more than what engineers understand. So in fact, there is this book by James Gleick, The Information, which appeared last year. He goes quite humorously into this point. It's a good read. This is a bit poetic. Einstein finds the relationship between mass and energy. Shannon finds the connection between energy and information. Yes, definition of continuous entropy is not as natural as the discrete one. The possibility of being negative makes it not very well clear to me. Innovative theory without being aware of all the problems that it can be applied to. Like, for example, I gave you the example of the constrained sequences, now very important for optical recording, magnetic recording. There was no way that he could have foreseen that at that time. How quickly I found application of principles and ideas in this paper to some things I've been working on recently. So I hope all these comments, if you haven't read the paper, you should make a point of reading it this summer. Reminds me of what Professor Toby Berger says during his information theory class. Don't try to make the problem fit your tools. Get yourself the tools that fit the problem. Good advice. Okay. The intuition rooted deeply inside two mathematical hearts, Isaac Newton and Claude Shannon. Rereading this paper is not about learning new theorems, but it's about seeing a vivid movie of how a great scientist found an important problem and how he devoted himself to solve it. Okay, now this one is interesting because you notice that I put it here in a different color. Imagine the code to be infinitely long. Okay, so don't make that mistake. Information theory is not about infinitely long codes. It's about codes that are born and die. Okay, with a finite lifetime. Now, shortly after this paper was a discussion about information theory, and they asked Shannon about this. Hey, but this is like, okay, we have to wait until hell freeze is over. He says, no. I mean, it's finite block length. It would be very difficult to find the answer to the finite block length, but if one can do it, it would be very interesting. So don't make the mistake of saying, okay, so because the results are limiting results, then they only apply to infinitely long codes. No, I mean, there is always a leap of faith here, because we have a limit, and then we have to believe that an actual system that may work at 1,000 bits, block length of 1,000 bits or 100,000, we have to have a leap of faith that tells us, yes, that in fact is close to the limit or is not close to the limit. And then there's been quite a bit of work in information theory trying to quantify how far from the limit we are. And in fact, I think Andrea in her talk is going to touch upon that. Okay, so here's the one, ZIL. This is the answer. S-Z-E-L-E. 1943. So I
As a
guess,
student?
yeah.
This was me.
Why are you people so surprised that students have all these smart comments? At least the ones we get in Princeton are like this. At least there's one there. Okay, so are there any other comments? Yes,
Why is H used for entropy? Why not E?
for H.
For entropy.
H.
Yeah.
So I was saying that Boltzmann, he never used H in his work, and in fact his tombstone. Let's look at that. Okay, so here, let's see. Yeah. This. Yeah. So. Well, it's kind of small, but you can probably see it there. His tombstone. S equals K log W. Okay. So in fact, they could have saved the K because they just depends on the basic probably the guy charged them a little bit more. But you see that it's S rather than H. But then when people refer to this second law of thermodynamics, they kept calling it the H theorem. So somehow, I don't know what was the reason. This S then became later on H. It might have been Gibbs, the first one who used the H, I don't know. And then it just happens that Hartley, in his 1928 paper, he also used H to denote the logarithm of the number of possibilities. So that's how it stuck.
I think Klaus used F, but that's something.
Yeah, Klaus is used S, yes.
And I think there is, and he used in a different setting, it's a differential of speed, the changing in time, something like this, and then you can find a relationship proving that these things are together. But I don't know where H appears, but there is equivalence there, physically.
So I read somewhere Kolmogorov's introduction to this paper was actually based on a really poor translation with lots of stuff missing and not translated well. Do you know about that?
No, I mean, the Soviet Union has these quirks that there were certain things that, for some reason, even in technical work, they didn't want to have translated. Okay, so, but I'm not aware that this was a particular problem with this. But for example, in cybernetics, indeed, that was considered to be a decadent kind of capitalistic product of the capitalistic imagination. And in fact, they were right with that. It didn't really pan out. There was a lot of BS there. That particular thing, I don't know. But he was quick to recognize how important that is. He didn't speak English. He spoke German, but so probably he had to really translate it.
Okay, let's thank Professor Verdú.